right, so we've recapped a couple of things that we've seen before. We've had another look at the temperature effect of the distribution of kinetic energies in a population. That should probably be a population of gas molecules. Solution effects a little bit more complex, but if you could do it in the gas phase, the math is usually easier in the gas phase, and it makes presentation of the bigger picture easier. So as you increase the temperature, you increase dramatically the population of molecules that are high in energy. And it's only the high energy molecules that are going to be capable of creating a reaction, because activation energy says there is a barrier to reaction, that the molecules have to have a certain amount of energy imparted into them before that reaction will occur. And we've seen those two concepts before. One of the things that isn't immediately obvious, lots of people don't know, is that the behavior, that little, it's a Boltzmann distribution that we showed the curve, and then the curve changes with temperature. Somewhere in like the 1960s, it was Merton, Scholes, Fischer-Black, Paul Merton, it can't be Paul Merton, Meyer and Scholes, Fischer-Black, I think maybe Paul Merton, were economists, and they mapped that scientific theory of how energy moves through a population of gas molecules to the way that money passes through a population of people. And it's the same math. It's the same math, that if you give a distribution of gas molecules energy, they don't get it, it's never shared evenly. There's an average, and some molecules are going to get less energy, and some molecules are going to have more energy, and then a tiny amount of molecules are going to have a lot of energy. And they're the ones that go on and do the superstar things, because they're the high energy molecules. Turns out to be exactly true for money. And we've seen it, we've actually seen it happen when in modern times a country completely changes its money. I think when the Berlin Wall came down in the 90s, or Iraq changes its money 20 years ago, that if you try and even the playing field, it takes about a day before the first millionaire is made. When the Berlin Wall came down, the east side of Berlin was a communist state, and everybody was forcibly told that they had to be equal to everybody else. And so everybody was kind of in some kind of suppressed poverty. Like a day after the wall came down, the first millionaires started popping up, because the distribution is not even. Nature is not nice and kind and even and socially minded. We see that with entropy. We see it now with energy distributions. Nature is cruel, and you have to combat it. Yeah, it can be beautiful and all of that stuff, but doesn't go the way that you might think. All right, so Svante Arrhenius is the first guy. Arrhenius' name pops up a number of different times in the history of chemistry, but this is the thing that right now we're going to deal with. Arrhenius looks at the rates of reaction at two different temperatures and relates what's going on. So the very first thing that he does is he relates the rate of the reaction, and rather than do that directly as a rate, he finds that mathematically it's expressed through the rate constant. He's going to relate the rate constant to the activation energy of the reaction. And it comes in a form of an equation. So this is his first, that K is equal to some factor A. Now A is called the collision factor or the frequency factor. It's not a number that we're ever going to go and track down. It's just a little bit tricky for us to get at. This is going to be over RT, not just over R. Yeah, it's over RT. Okay, so let's define what we have here. K obviously is the rate constant. And the units of the rate constant depend on what type of rate it is. A is something called the collision factor or the frequency factor. And what that is, it's a quantification of how many high energy collisions does my population have. EA, we've seen that before. That's the activation energy. That's that absolute barrier that you have to have, that you have to overcome, otherwise your reaction won't work. R is the gas constant. R is the universal gas constant. And we, about 2/3 of the way through, or 3/4 of the way through chemistry 1, we did gas laws, and R is in a lot of those gas laws. PV equals nRT. That's the same R, but it's in a different form. R shows up in a number of calculations, and when it relates pressure to volume to temperature, it has a different volume, it has a different value. That's the 0.0821 liter atmospheres per mole per Kelvin version. This is the one that relates energy. So if you ever see R written down in a calculation that relates something going on in the gas phase to energy, it's going to be in this form, which is the 8.314 joules per mole per Kelvin. Now, we often see kilojoules per mole, all right? There is a K in here, but that K is not at the beginning. These are not kilojoules, this is joules per mole per Kelvin. And T is our temperature in Kelvin. Okay, so this is what he used to relate this useful number to that kind of hidden number, and right now, this is just at one temperature, and that is a number that is outside of the scope of general chemistry. We're not going to go hunting for that. If you come back for maybe physical chemistry at a higher level, we'd go and dig for this, but not right now. Okay, so that's great. I had a quick look through the textbook, and the text seems to be completely hung up. Whoever wrote the book seems really concerned with finding activation energy, which is not my interest at all. My interest is more real world of, okay, I can relate rate through its rate constant to temperature. What if I change the temperature? What would that do to my rate? So we could set this up in parallel and do the equations twice. Or we could kind of derive one calculation formula that does everything for us, which is what we're going to do now. So this way, this form of Arrhenius' equation, I have never ever used. Not ever. It's never come up. I think it's much more useful to predict K at two different temperatures. Oh, obviously there is something in this formula that didn't make it into our little sidebar of what all the terms meant, and it's the E. That's the exponent. That we're going to make that go away. How'd you make the exponent go away? You take the log of it. Yeah. So I'm going to take the log of this whole equation. And so now it'll be lnk equals just this term, right? And then I'm going to splice them together. So E is our exponent. All right, let's do that. So if I take the natural log of K, so what I have to do is now, I can't do it just on one side. I'm going to take the log of this side, which means I need the log of the other side as well. So if I take turn K into the natural log of K, that means I have to take whatever A is into the natural log of A. Don't get this confused right now. We've been using concentration of A as a term up to this point. This is different. And then this exponent goes away. I stepped on my cap right there. Okay. Now, if I just rearrange this a tiny bit, I get ln k equals, so what I'm going to do is I'm going to take this term, which we always write, usually if there's a positive number and a negative number, we usually write the positive number first and the negative number last, because Isn't that always, that's how you taught to do subtractions? Big numbers and then subtract the other number from it, right? Gonna switch them. If I switch minus EA plus, so minus EA over RT plus ln A, doing it for a reason, it'll become apparent in a second. And then do something really, really sneaky. Take away the t. And I multiply EA over R by 1 over t. That's the same term. All I've done is split it. It's going to become obvious why I'm splitting it in just a second. So this equals that, which is equivalent to the very first thing that I wrote down. Yes? Okay. What do you think the proportionality between ln k and minus EA over R times 1t plus ln A looks like? It's a straight line. If I plot ln k against 1 over t, natural log of k just became my y. 1 over t just became my x. B is going to be my y-intercept, which is going to be on the vertical line, and will have the value of the natural log of whatever my frequency factor is. And then I'm going to have a slope. And that slope is going to be negative, downward facing. And its gradients will be EA over R. So we can find the activation energy, because R is a constant. It means I can find the missing number. There, right there is the natural log of the collision factor, the frequency factor, and my slope is the activation energy of the reaction divided by the gas constant. Okay, that's useful. Okay. Let's do that twice. At 2 temperatures. I'm going to write that down twice. With the T1 for my first temperature, that will have its own rate constant. Because remember, rate constant needs to be quoted for every specific temperature. You change the temperature, you actually change the underlying rate constant. So if I do 2 of these, at temperature 1, I will have the natural log of my first rate constant is equal to, which way am I going to write this out? Yeah, it doesn't matter. It doesn't matter. We're assuming that the activation energy for my reaction doesn't change. Why should it? And with the gas constant doesn't change. Why should it? at the temperature 1 plus ln A, and then here, under the second scenario, the natural log of K2 is equal. Okay, so here are my two scenarios. Temperature 1, temperature 2. Both in Kelvin, although they might not be in Kelvin in the question that's given to you, in the problem that's given to you in the book, or on the test, or on the quiz. That's just something that's an obstacle for you to get over. At this temperature, I'm going to have this unique rate constant. That temperature, I'm going to have this unique rate constant. And these two separate Arrhenius equations tell the story. I'm just going to take line 1 and subtract line 2 from it. If I do that, then I get, I'm going to do it 1 over 2. Now it actually doesn't matter whether you did 1 minus 2 or 2 minus 1. It doesn't matter. And sometimes when we're using the Arrhenius equation, the one that I'm going to get to, I'm going to compile this down and derive it into something really, really sweet in just a minute. Sometimes when we're using it, because there's a log in here, the log of any number that is less than 1.00 goes negative. So if you have set your equation up with the little number divided by the big number, all of your numbers are going to be negative right to the very, very end, right to the last step of your calculation, when the negative on the left-hand side of the equation and the negative on the right-hand side of the equation cancel each other out, and your number pops out positive. Okay? If we're looking for temperatures, your number's never going to be a negative number. You can have negative numbers in Celsius and in Fahrenheit, but you cannot have negative numbers in Kelvin. It's an absolute scale. Okay? So sometimes when you're doing this, you're going to wonder, I can't possibly be on the right track because everything I do is negative. Well, don't worry, it will right itself, but it waits right to the very, very end. And if you do it the other way, with the big number over the little number, it feels better while you're doing it. It looks like it's reading correctly, but you're probably not going to do this wrong. Okay, so now, well, that part's easy, because it's just this minus that. This is a bit uglier. So I got the first term right here, plus ln A minus EA over R. Oh, I forgot the T's. T1, T2, plus ln A. Okay. So I'm going to break these things apart. And that ln A, when you subtract that ln A from it, it's going to go away. These two terms, they're going to go away. And that leaves me with minus EA over RT1 minus, right, I'm going to write it out twice, minus EA over RT2. Okay? This term, ln of the frequency factor, minus the natural log of the frequency factor, they're cancelled. The negative EA over RT1 minus EA over RT2, A minus of a minus gives me a plus. So I'm going to put a plus term in there now. And you remember from yesterday what happens when you take two logs and you subtract one log into the first? What's the trick that we can do there?
You divide.
You divide the underlying numbers and take the log of the whole thing. And this is starting to take shape. That the natural log of k1 minus the natural log of k2 is now equal to the natural log of the ratio of k1 to k2, which is a beautiful thing. Because I have just changed your world from having to know what these two numbers are. Under this line, you had to know what ln of k1 is so that you could subtract ln of k2 from it. You don't need to know now. All you need to know is what the relationship is. This one's twice as fast as that one. So instead of having to know the numbers, now we can know the relationship. This is cool. All right, I'm going to do the thing with 1 over t right here. I'm going to break the 1 over t out into its own separate box because it's my x quantity. And I'm going to do the thing also where I took the negative term that was here and put it at the front. I'm now going to take it and I'm going to put it at the back. Okay? So ln k1 over k2 now equals, if I put that at the back, it would be EA RT2, which I could do. Right? Instead of just saying it, I'm going to show you. EA RT2 minus EA RT1. Yep? All right. Now I'm going to break out the t's as their own separate thing. So I get EA over R done. That's my formula. The relationship of the rates of two reactions done at two temperatures is the rate constant of the first one divided by the rate constant of the second one. I'm going to take the log of that. Activation energy, it's written down somewhere. Gas constant, it's written down somewhere. Temperature 2, temperature 1. Okay, the only thing to be cautious of is this is K1 over K2. So the first number that you write down is K1. The temperatures come T2 minus T1. So it's 1 over 2. It don't knee-jerk this into being 1 minus 2. It's 2 minus 1. We're going to flip those numbers around. Okay? This is what we're going to use. This is how you use the Arrhenius equation. This is what it's set up to do. Some other stuff is nice, and it has to be in the textbook because it's fundamental, it's a landmark. But this is where all the real practical application exists. So let's do some. Do some questions. And this is nice. This is why it's set up this way in the first place. But I've never used the K equals frequency factor exponent negative EA over RT. Never used that form of his equation before. Okay. What have I got? I got a couple of questions. Let's see if it makes sense which one I should do first. The first says, what would the rate be at a new temperature? The second one says, how much faster would it be at a different temperature? Which is kind of the same question, but subtly different. And then the last one is, what temperature would I need in order to make this go twice as fast? I'll just do them in the order that I've got them written down. And again, not so many questions from the end of chapter questions in this book. The book was preoccupied with finding activation energy, which is something I've never had to go digging for this way. I've always done it some other way. This pen's getting a little bit faint. Let's see if I've got another black marker in my bag. Got lots of blue ones. Nope. Okay. Try blue. All right, let's just read some questions. A reaction has an activation energy of 160 kilojoules per mole. At 190 degrees Celsius, the value of its rate constant is 2.52 times 10 to the negative 5 per second. It's a first order rate reaction, but our days of having to worry about whether this is a first order, second order, or whatever reaction and matching the mathematical model to it, not for this. Arrhenius works for everything. Don't have to worry about whether it's first order or second order. That's a first order rate equation though. Okay, here's the question. What would rate constant be at the new temperature of 157 degrees Celsius? Okay, so we're given data that is universal to the reaction. That's my activation energy. And then I'm given some specific temperature, specific information that at 190 degrees Celsius, my rate constant is this number. At the new temperature of 157 degrees Celsius, there has to be a new rate constant. Go ahead and find it. Okay. Get into the habit of writing this out. So on the test, I'll give you some information. I'll write R equals 8.314 joules per mole per Kelvin, but I'm not going to write what the form of the Arrhenius equation is at two different temperatures. I'm not going to give you the formula. You have to know that. Down. We're at the position now where I have 1, 2, 3, 4, 5, 6 quantities in my equation. I have to know 5 of them in order to find the 6th missing number. I think we should probably keep track of them, because if you don't keep track of them, you run the risk of putting K1 and K2 in the wrong place, or T2 and T1 in the wrong place. So K1 equals, K2 equals, EA equals, R equals, T1 equals, T2 equals. This is just good housekeeping. It's prudent to do this. Okay, K1 be the value of the rate constant at the first temperature. Now, at this point, nobody is holding your feet to the fire and saying, oh, the first K in the question has to be K1. You could look at this and say, T1 is a bigger number than T2, therefore I'm going to have T1 be 190 degrees, therefore K1 will be the number that matches it. Okay? Doesn't matter. Or you could say, oh, I want this to be a temperature increase, therefore I want the smallest number to be T1. Okay? Doesn't matter. Just as long as they go into the equation in the right slot. Doesn't matter whether you take the big number from the little number. This is a smaller number than that, this log goes negative. If this is a big number, and that's a small number, then 1 over a big number is itself a smaller number than 1 over the slightly bigger number, right? And therefore this term will go negative. But they're going to match each other out. It will match. Okay? So K1 gets to be 2.52 times 10 to the negative 5 per second. K2, I don't know what K2 is, that's what I'm supposed to find. EA is written in the question, and it is 160 kilojoules per mole. R is 8.314 joules per mole per Kelvin. T1 is 190 degrees Celsius. Now, we don't use Celsius in mathematical calculations. We learned that when we did Charles's law, where we related volume to temperature. If you use Celsius as your temperature scale, at some point, temperature can become a negative number, which would mean, because volume and temperature are directly proportional to one another, that your volume also just went negative. You can't have a negative volume. There's no such thing. Volumes are, by definition, three-dimensional and positive. You can't have a negative volume. Therefore, we cannot use Celsius as a temperature. It has to be Kelvin. Our numbers cannot be allowed to go negative in our calculations. So, what's my conversion factor to turn Celsius into Kelvin? Yeah, I'm going to add 273.15. Don't have enough precision to worry about the decimal after that. So plus 273 equals that's 463 Kelvin. And my other number is 157 degrees Celsius. I'm going to add 273 for that. And that comes out, oh, that's kind of convenient. The 7 and the 3 coming out to be a whole number right there. 430. Okay. So we can start putting numbers in. The temperatures are both going to be in Kelvin. The rate constants are both going to be in per second. So all I've got to do is make sure that I haven't got something funky going on with my activation energy and my gas constants. gas constant is in joules per mole per Kelvin, and the activation energy is in thousands of joules per mole per Kelvin. It's in kilojoules. That cannot stand. We have to make those two be in the same factor. So either I convert my kilojoules per mole to joules per mole, so this cancels. Oh, there's a -1 missing there. Or I convert the gas constant down to kilojoules. Multiplications are easier to do than divisions. Your eye will scan them better, less likely to make a mistake. Okay, so 1,000 joules is 1 kilojoule. So if I take that number and multiply it by this factor, I get 160,000 joules per mole. That's the number that's going in my calculation. Okay, ln of 2.52 times 10 to the -5 over K2 equals 160,000 divided by 8.314 times 1 over 430 minus 1 over 463. Now you could probably just pump all those numbers into your big fancy calculators these days and come out with an answer. I do like to break it down step by step, so that when you read it back, it makes sense. So we're going to do it the long way. 160,000 divided by 8.3 turns out to be 1,925. And then I'm going to multiply that by this number. Did I put them in the wrong place? Hold on. Oh, you know what I've done? We're going to go on a journey because my solution has K1 over K2. I've switched the numbers around. It don't matter. It's still going to work out. So this is what, 1 point, tell me what that number is, because I don't have it. I did it the opposite way around. I made this be K2, and I had K1 be my number that was missing. So what is 1 over 430 minus 1 over 463?
.00016.
So how many zeros?
3 zeros after the decimal place.
So that's 10 to the -4. And what were the numbers?
Well, I had 166. Did you do 3 zeros after the decimal place?
Yeah, I'm just doing this.
Okay.
Oh, yeah, because 10 to -4, you count the 0 in front of it. Okay, so guess what happens if you made K1 be the unknown quantity, and K2 is here, and 463 is here, and 430 is there. That's the same value, it just has a negative. And I'm putting the negative somewhere else in the equation. Okay, this is what we talked about. So this one's going to stay positive. My solution had a negative in it all the way through. Okay, so the numbers are going to remain the same, which means that the natural log of 2.52 times 10 to the negative 5 over K2 equals, smash those two numbers together. On my page, it's a negative number because I did it upside down. Here, it's going to go to be the positive number. That should be 3.175. Keep that unnecessary precision in your calculation. Only round up to the significant figures at the very, very end. We're going to do a log to exponent conversion in a minute. Take the anti-log, and we want to keep as much precision in this number as possible. Don't go rounding now before the log function is kicked in. Okay, let's take the log part away, which tells us that 2.52 times 10 to the negative 5 over K2 is equal to that value. I've made the log go away. Take the exponent of this side, the exponent of that side, makes this log function go away, just gives me this fraction now. So you've got to get used to where that function is on your calculator. Everybody's got a different brand and a different model, so I can't help you with everything. That's something that you're going to have to figure out how to achieve on your own. And that is a number that I currently don't know, because at this point my numbers deviate from your numbers. They will reconcile at the very end, but I've got the inverse of what you've got. So 2.52 times 10 to the negative 5 over K2 equals the anti-natural log of 3.175. So the e to the x button is probably the second function on the same button as your natural log button on your calculator. And if it's not, it's probably close to it, because they usually group them together. Do we have a number yet? I have to break out my own calculator and do it. Okay, so for me, it would be second, this 3.175 equals, I see 23.93. Is that different than anybody else? Nope. Okay, so if this number divided by K2 equals this number, what does K2 equal? Just move those two. They will switch position. 2.52 times 10 to the negative 5 divided by 23.93 equals K2, which equals It's the same number. So I did my calculation on paper, the one that I was going to show you, a different way. I had my K1s and K2s switched and my T1s and T2s switched. So on my page, this number was a negative number and that number was a negative number, but they reconcile right at the very last step. Yours stayed positive all the way through, but you end up with the same number. What's the number?
1.05 times 10 to the negative 6.
Yeah, it's a really small number. So what's my biggest? 3. We're going to go with three significant figures. 1.05 times 10. Lots of zeros in front of it. If this is a 10-point question, how many points have I earned up to this point?
9
9. What am I missing?
per second.
The number itself is absolutely meaningless without the units. How far is it to get to the city that you live in? 3. 3 what? 3 days walk? 3 miles? 3 kilometers? 3 hours drive? I don't know what you're talking about. Because you haven't made your answer relevant. Okay. All right, so first pass through is going to be the long one. Let's do this twice more. I'm going to do this again with 2 questions. My next question is the same question with a slightly different spin. My next 2 questions don't have unique numbers. They ask about the relationship. What would I do to make this 10 times quicker? What would I do to make it 2 times quicker? How long would it take to be 2 times quicker? That's the beauty of the way that this equation is set up, is that you don't need to know all the individual numbers. Next question is, I got at least one out of the textbook. 1457, this is out of the textbook. (1457) says that if your activation energy is 65.7 kilojoules per mole, how much faster will reaction occur? At 50 degrees Celsius than at 0 degrees Celsius. Okay. We've got the equation. We've got our little table. Let's put the numbers that we can divine from the equation, from the question, in to our table. Okay, first things first. R is a constant. I do not need you to memorize constants. Constants are constant, and so somebody has got it written down somewhere. You shouldn't have to memorize it. So that number will be available to you. It'll be written on the test, not necessarily in the question. but on the test somewhere, maybe on the front page. Activation energy, written in the question. It said 65.7 kilojoules per mole. So I've done this once. Not going to get tricked by that. I need to multiply that by 1,000 to get joules per mole to match the units used in R. Temperature. My temperature runs from 0 degrees Celsius to 50 degrees Celsius. So my first temperature is 273 Kelvin. And my second temperature is what? 323 Kelvin. Okay. What's K1 and K2? I don't know. I don't know. That's what I'm being asked to find. Now, that would normally freak me out. That there are two missing variables. I can't solve for two variables at the same time. Can't solve for two things. Give me one. Oh, it's a ratio. This is actually easier than the previous example because we don't have to do anything beyond find what this chunk of number is. The question is asking me to find the ratio. How much faster will the reaction be? In fact, if it were faster, we should have put the bigger temperature on the top. See that? Again, we could do that. We could change now before we've written it all out. Is that the way I'm going to go? T1, 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 T2, T1. Yep. Okay, let's do that. Here's what we want. We want this number to be big number divided by a little number. The question says faster. So what I want is the K1 to be the fast one and the K2 to be the slow one. Okay. Now if I do it the other way around, that's okay. It'll give me a number. And what I have to do is turn that number upside down. But let's plan. Let's plan. I want the number reveals to me. I want at the end of the day to find out what K1 over K2, that ratio. So I want K1 to be the fast number and K2 to be the slow number, which means that T1 is going to be the hot temperature and T2 is going to be the cool temperature. Okay? So, before we start pumping our numbers in, let's just change those two around. The math would work fine either way, only if we did it the way that I had written it in our table right here, then I would have to invert my answer as the last step. This way I don't. So a little bit of planning, make that big number divided by little number, will reveal that this is actually accelerating, that it's speeding up. Okay, let's put the numbers in. So the ln of k1 divided by k2 is 65,700 divided by 8.314 times 1 over 273 minus 1 over 323. That should work. Okay. 65,700 divided by 8.314 is 7,902. And 1 over 273 minus 1 over 323 is 5.67 times 10 to the negative 4. So the natural log of the ratio that I'm looking for is 4.481. Okay. Natural log of the ratio that I'm looking for is 4.481. That means I take the antilog, the exponent, that my ratio that I'm looking for is this term. Find that on your calculator. All we're looking for, and then we're done. That's it. We're only looking for the ratio. Get a number? What's the number? 88.3. Yeah, 88.3 sounds good to me. Let's write that in. So K1 over K2 is 88.3, which tells me that the reaction goes about 90 times faster. At the new higher temperature. Okay? Okay. Now, if you'd have done that upside down, you would have, your answer would have come out as 1 over 90. And you go, whoa, my reaction's getting slow. Oh no, look, I put my temperatures the other way around. Okay. So I did little number divided by big number instead of big number divided by little number. So take a second, take a breath, take a second, and this should help. You're actually mapping your question out. So there are 2 numbers missing here. Doesn't matter. Doesn't matter that I need 2 numbers, because I only need the ratio of K1 to K2. Don't need the individual numbers. I only need to know what they are in relation to each other. Okay, one more. One more, we'll take a break and we will be done. Am I going to say no more math? No more math for the rest of the day after this. Okay, we're going to go out on a flourish. After this, it becomes conceptual. I think at this point there is plenty of math for the first test. You've got half-lives, you've got Arrhenius, you've got concentration to time dependency, you've got finding a rate law, a bunch of stuff. And then you've got M1V1 equals M2V2s, dilutions. Okay, here's a question. I think I might just have co-opted a previous question and kept the numbers in. So again, we're going to use the same activation energy. If the activation energy is 65.7 kilojoules per mole, that's one less thing to erase from the board. And the temperature is 25 degrees Celsius. What temp will cause reaction to go twice as fast? Okay. My questions are having progressively less and less content in them. It started out, the equation is written that it needs 6 numbers in order to complete. So with 5 of those numbers, you can find the missing number. This question only has 2 numbers in it. It has an activation energy and an initial temperature, which tells us we don't necessarily need to know the individual numbers. This is set up to tell us relationship. Okay. T1 or T2? T1 or T2? I'm going to have T1. I'm going to assume, so my reaction is currently at 25 degrees Celsius. I'm asking you to find a new temperature at which the reaction rate will be twice as fast. Is that number going to be a higher temperature or a lower temperature than I'm currently working at? Higher. Because increasing temperature increases reaction constant, rate constant. So I'm going to go ahead and make my first temperature be the 25 degrees Celsius. Second temperature, I don't know. That's the thing that's being asked. So 25 plus 273 is 298 Kelvin. The EA has been converted into joules per mole. The R is already in joules per mole per Kelvin. And then K1 and K2. What's the value of K1? I don't know. What's the value of K2? I don't know. What do I know? What do you know about the values of K1 and K2?
The ratio of K1 to K2 is 2.
K1, whatever it is twice as big as K2. Tells you in the question. The reaction is going twice as fast. Therefore, the rate constant for K1, ooh, wait. What do I want? Do I want the big number on the top, or do I want the big number on the bottom? It doesn't matter. It doesn't matter. If I T1. T1 belongs inherently with K1. Then T2 at the higher temperature will be the higher rate constant. If I turn it the other way around and I made K1 be 2 and K2 be 1, then the 25 degrees Celsius has to be T2. It doesn't matter. It doesn't matter. Or 2 over 1. So this is going to be 1 over 2. Or you could do 2 over 1 and have that number be the unknown and this number be the 298. Okay? Just get the relationship right. Okay. So the first time we ran through this, everything was a positive number. The second time that we ran through this, we made it on purpose so that the big number was over the little number because we wanted to know how much bigger stuff was going to get. Let's do this one upside down. K1's the little number, K2's the big number. This gives me 1 over 2 instead of 2 over 1. My log of that number is going to be a negative number. Don't care, because that's going to be a negative number as well. This is going to look a little bit uglier than doing it the other way, but it's worth doing it upside down just to prove that it doesn't matter. Okay, I'm going to have negatives on both sides, but they're going to cancel each other out. So that one is the fast one, and this one is the hot one, okay? Fast goes with hot, cold goes with slow. Just make sure that they're lined up, and it doesn't matter which ones you pick, just as long as they're lined up. Okay. That gives me that the natural log of 1 over 2, I've said 1 over 2. You could pick any number out of your hat. You could make that 150, because 100 is twice as big as 50. 200 is twice as big as 100. Okay. Equals 65,700 divided by 8.314, which we conveniently already know what that contracts down to because we're using the same numbers as the previous example. Now, just make sure that these are in the right place. 1 over T2. T2 is my hot temperature, and I don't know what it's going to be. Subtract from that 1 over 298. Okay, that's how I'm going to set up my calculation. If any of you are nerds or geeks, you will know what the natural log of 1 over 2 is without having to look it up, because we did it yesterday. What's the natural log of 2?
1.
No. 0.693. The half-life, that's the half-life number for a first order reaction. Remember the half-life? T half in a first order reaction, T half is 0.693 divided by K, because the natural log of 2 was 0.693. So what would the natural log of 1 over 2 be? Negative 0.693. Don't want to get all mathematical. There is math in this in Gen Chem 2. That's the way that it's set up. not teaching a math lesson, teaching a chemistry lesson. Somewhere under all these numbers there is chemistry. Okay. But understanding a little bit more about log behavior is to your benefit, because your calculator is going to spew out a number and you're just going to accept it. At some point you should go, yeah, I understand why that would be a negative number. It's less than 1. It's supposed to be a negative number. And I kind of sort of remember that the natural log of 2 was 0.693, so the natural log of 1 over 2 should be the negative. Okay, what did that 65,700 divided by 8.31 was 7902. We're going to multiply that by 1 over T2 minus, I haven't collapsed that down yet, but I believe that's I don't know yet. Okay. I have a number. I have a multiplication term multiplying all of this. So if I move this across the equal sign, it goes underneath this term right here. So 0.693 minus divided by 7,902 equals 1 over T2 minus 1 over 298. At which point I'll be able to get rid of this term and have something that just tells me 1 over T2, and that will lead me to my correct answer. Okay. So that then simplifies that number right there. Is 8.77 times 10 to the negative 5 is equal to 1 over T2 minus 1 over 298. Oh, is this negative? Yeah. That was a negative number divided by a positive number, so my number stays negative. Okay? So negative, we told you there was going to be a negative in there. There's also a negative building here, but I'm going to move it over onto the other side. 1 divided by 298 is 0.00335. Yep, okay. So I have a negative on this side, and I have a negative on that side. I had warned you that that was going to happen because we had our numbers kind of upside down in the question, but it doesn't matter. It's all relative. I'm going to isolate this term by taking this number and moving it across the equal sign, in which case it will go positive. So 1 over T2 is now, this term becomes positive, 1.00335 minus a very, very small number. Times 10 to the negative 5 means 0.0000 before that first 8. So I'm taking this number, and that 8 is only going to subtract from 1, 2, 3, 4, 5, from here. It's only going to start subtracting from, oh, they're going to start subtracting from here. It's not going to have much of an impact at all. So what have I got? 0.003268, way more precision than I'm allowed to have, equals 1 over T2. Switch this around. Therefore, T2 is 1 over 0.003268. T2 equals 306. 306 what? Kelvin. What is that in numbers that relate back to the question? Because the question was in Celsius.
Thirty-three.
33 degrees Celsius. Is that right? Okay. So I start at 25 degrees Celsius. If I warm that reaction up an additional 8 degrees Celsius, it goes twice as fast. Okay? Be prepared for this question. This question is absolutely on the test in a form that you will have to work all the way through. Okay? And that involves you figuring out which numbers to put where, changing the units to match, not panicking when you do it upside down, because it ultimately will lead you to the correct answer, and then rationalizing your answer. Yeah, it came out at 306. Okay, that's fine, because your number should be in Kelvin, but the question was in Celsius, and your answer has to be higher in Celsius than your start point. So just say, yeah, I'm okay with that. All right, let's take at least 10 minutes of a break. When we come back, we'll do some conceptual stuff for the rest of the chapter, the rest of the day.